I'm going to talk to you about an in silico toolbox for hazard prediction of ENM chronic effects. This is the work performed in WP6 or Patrol. The highlight of the achievement in our work package 6 are as follows. We have created a Patrol database. We developed model from exposure to dose, such as the PPK model and the in vitro dosimetry model. We also have developed models that take you from dose to response, such as the QSAR model. Then the extrapolation of everything we know from in vitro to in vivo. And finally, the environmental modeling. Now, to start off, I talk briefly about what we have achieved in work package 6 in relation to database. And the database is currently available. You can see that from the link here. Currently, only Patrol partners can have access to it, of course. If you need to have access to the Patrol database, please write to the IOM and we'll let you have access to this database. There's very limited external partner access, and it had to be done through data sharing agreement and approval by the coordinator. The data will be made openly accessible after the embargo period, probably 2 years, as confirmed by the coordinator. There are also data from previous projects currently available in this database. The final steps that we have here is to finish this off. We are still uploading the last bit of the data from Patrol into the database, and we do that by communicating with the developer in NanoMap just now. We're preparing the final version of the data management plan, and we're writing the user guide for the use of the Patrol database. For PPK modeling, the main goal of the model is to support the experimental data design for in vivo dosimetry modeling. The develop and to refine physiological based kinetic modeling to conduct delivered and retain those estimations at the tissue level, and to improve our understanding on the nanomaterial dosimetry modeling, such as in vitro to in vivo extrapolation, which can be facilitated. There you can see the result we have for cerium dioxide for inhalation exposure and for oral exposure. And for inhalation exposure, you can have the lung burden and the liver, and for oral exposure we have data for the spleen and the liver. And the model, using the right parameter, it will be able to estimate the retained dose in these different organs. And here we have data for the lung and the liver with respect to titanium dioxide. This is inhalation exposure. Again, the model can simulate that. So on top of this model, RIVM has developed a web tool that includes this model. And it was developed to create a public platform that allowed the user to apply the PPK model, implement it and parameterize using the data that we have just shown you. It's currently there are two different materials. You can see the cerium oxide and the titanium oxide, the titanium dioxide. You can see them in the last slide, and they are available for single inhalation exposure as well as repeated inhalation exposure. The user can specify the airborne concentration, the lung deposition fraction, and the physiological parameter of the rat, such as the breathing rate and so on, and obviously the exposure condition. The web tool, once you input this parameter, it will be able to calculate the organ burden of the lung, liver, kidney, spleen. In addition, it will also calculate the amount of nanomaterial in the lung per unit surface area. And here you can see on your left here are the input screen to this web tool. So you can put in the various experimental conditions to the left, the rat physiology and so on. You'll be able to generate the lung burden in the different organ for you. Now we move to the in vitro dosimetry, and here we also generate a software, and recently there's been a workshop to show you how to use it. And the model for in vitro dosimetry consists of actually 3 peer-reviewed models: the ISDD, the ISD3, and the DG model. What we have done here is to convert the input parameter for each of these model into a common form that is suitable for all 3 of them, and allow the evaluation of each model's robustness to different specific application by fitting it to the experimental model. So you can choose the different model to run, and all this model apply to a physical dimension of a in vitro setting with a different bottom conditions, such as the gelatin coated bottom or the sticky boundary condition. And what it does is it generates the cumulative dose that reach to the bottom of the cell in time. So you can have that for different type of particle with different kind of physical chemical characteristics. And we must say that this model prediction fit the data very well, and you can see the goodness of fit here very high for both for TiO2, BSO4, and CO2. In addition to what we have done for the flat bottom type of in vitro system, we also try to estimate the dose deposited on the spheroid, and this is the final part of our work at in modeling in vitro, and we have to assume that the spheroid stays static, which is not the same as with the real condition in which the spheroid actually move randomly in the in vitro system. And so there are a few challenges for us is to somehow try to accommodate this randomly moving construct, but at the moment we are at the static construct just now. And the challenge for us is how do you actually model the uptake kinetics in a 3D dimension constructs as such. And at the moment we do not have the data to actually validate our model prediction. However, we have done our best in here, and assuming a static spheroid, we're able to calculate the amount of particles that are deposited on the top of this surface. As you can see in this heat map in here, you can see that as you drop on the top of the spheroid, obviously the highest concentration is the top there, and then it diminishes as you move out to the level of the radius here at the high point, the radius here that we have. And also we have applied the in silico model on in relation to scaling with respect to body size of different living organism, and this we use the environmental data from the University of Leiden, and we try to determine the scaling relationship between the toxicity effect caused by certain NP dose and the body side of the living organism. And you can see on the graph to the left here, you have the plant, the mammal, bird, blood, the whole set of living organism. And if you can look at the log of the body side versus the local toxicity, you can see there's a nice correlation here. Then we move on to the QSAR methods that has been used in work package 6, and we make use of the BMD values in relation to experimental transcriptonic BMD value for the granulocyte adhesion and diapedesis pathway that is perturbed by multi-wall carbon nanotube. Okay, so this approach here is for multi-wall carbon nanotube, and we have a nano QSAR model that tries to link the structural characteristic of the material with the dose that induce the transcriptional perturbation in that selected pathway. And in order to do that, we need to calculate the descriptor, which is the structural characteristic of nanomaterials such as length, diameters, specific surface area, etc. And for the response, you have the gene expression. So we attempt to grouping of multiple carbon nanotube by looking at the principal component analysis in the space of gene associated with this pathway, and we look at it pointing out the genes that are upregulated or downregulated. And we're pleased to show that a simple descriptor such as a combination of length and diameter of the carbon nanotube was able, using these two characteristics, we're able to predict the value of the BMDL for your multi-wall carbon nanotube. In this case, we calculate it to be 12.27 microgram per mouse. Okay, then we use this approach to predict the lowest bound of the benchmark dose for transcriptomic pathway. And as we say, we also use here we use the principal component data analysis to look at the data that was generated by the high throughput data analysis for BS cell, A549 and HepG2 cell. And you can see that between the first and the second principal component, we're able to explain most of the variation of the data in here for these three different cell types. So the principal component analysis for the similarity of the induced biological effect as expressed by cell viability, cell number, DNA damage, nucleic acid oxidative stress, and apoptosis. So we are able to use it and try to determine the relationship between the biological endpoint and the toxicity expressed by all these nanoparticles. So what is the relationship between the biological endpoint and the toxicity expressed by the ENM, the result of the high throughput data analysis? We discover that there's different sensitivity of cell line to the toxic effect of nanoparticle. And NM300K expressed the strongest adverse effect among all investigated NM independently of the cell line. The BS2B is most sensitive to silver, then zinc oxide, then titanium dioxide. A549 is most sensitive to silver, zinc oxide, and carbon nanotube. Well, the HepG2 is more sensitive to silver and zinc oxide. So there is a clear pattern in here, with silver being highest rank, followed by zinc oxide, and then at the lowest rank you have titanium dioxide and carbon nanotube. But also we notice that there is batch to batch differences, and different batch may express varying toxic responses. And our analysis indicates the differential response between normal, such as BS2B cell, and cancer type cells, such as A549. Now we move on to the comparison in vitro, in vivo, and here we aim at the fibrotic responses, where data from alpha quartz are most rich for this kind of comparison. And later on, using the technique we developed with alpha quartz with the and minusil, we then extended to apply to CO2, TiO2, and BSO4. And we focus on fibrotic responses because it's linked to increased pro-inflammatory mediator, pro-inflammatory cells in tissue, as in the fibrosis AOP. And this will provide a potential opportunity for in vitro and in vivo dataset comparison. And you can see our first attempt is to look at the relationship between PMN responses and fibrotic score, and you can see a very nice correlation between PMN response and fibrotic score here. And again, we also try to relate fibrosis to exposure of quartz, and we notice here that 10 milligram per meter cube often is the lowest limit of alpha quartz exposure required to induce fibrosis, independent of the amount of post-exposure time. So you get fibrosis even after a short post-exposure time or a medium or very long post-exposure time. This is the lowest you ever get fibrosis materializing. If you move below 10 milligram per meter cube, that's nothing. And in order to link the dose to the PMN response, you can see here is the relationship between the dose as lung burden versus the PMN response in vivo. And where there's no such a lung burden, we use the MPPD model to calculate the amount of dose deposited in the lung. And here again, you can see a nice correlation between the calculated dose using the MPPD model and the PMN response. It's very similar. However, we notice that IL-1 beta is the one that correlate the best with the in vivo PMN and in vivo PMN installation. Okay. You can see in here from this graph here that it's now possible to scale the in vitro and in vivo dose basically by a division by 100 to bring the in vitro dose down to the same level as the in vivo dose. So in conclusion, also IL-1 beta, IL-6 and TNF alpha measured in vitro correlated with the PMN response in vivo. It gives us the promising endpoint that we can use to align the in vitro and in vivo study. However, we must put a caveat in here that this is not always consistent across cell type or test model. And this is still based on a few individual studies that the data are available to us. So there is a limitation on the data available for the kind of suitability for analysis. And of course, there's a limit in the number of doses that we use here. And also there's a huge variation in the reporting of the physical chemical characteristics of this particle. So there's a lot of uncertainty that ongoing behind all this data. And of course, in order to do a better job, we need more data points, both in vitro and in vivo, for better use of the BMD modeling. and we need a standardized methodology and reporting so that we can benefit future efforts in extrapolation in vitro, in vivo. Now we move to the environmental modeling. Here, that our challenge is to develop methods for extrapolation of the EC values, such as EC50 to EC20 for various species and endpoint. There are some challenging basic assumptions, such as the similarity of the mechanism of the toxicity, the shape of the dose response curve not affected by the medium composition. So we have taken the following step to collect the dose response data, in this case the immobilization of the magna, and we use quasi QSAR for modeling, and we have the Monte Carlo simulation method to incorporate the different conditions. Well, it is quite nice to report here that the model should to predict the EC value with accuracy of between 95 and a standard deviation of 2.3%. This is very good. And for an independent validation set, the standard error between prediction and observed is only 3.5%. So this is independent prediction versus a kind of estimation that you see in point 1. So finally, as I explained as in the QSAR, we are able to do all this analysis thanks to the high throughput screening that MISVIC has done to generate a dose effect curve for 23 nanomaterial encompassing over 75,000 data points. The composite output addresses 20 biological endpoint relevant for cytotoxicity MOA analysis and for in vitro, in vivo, and AOP modeling. You know, helping task 6.1 and 6.6 with the modeling of raw and derived data, as well as result analysis for training protocol has been delivered by MISVIC for the use of the other modeling effort as reported earlier. So finally, this huge data set is also part of the database and can be references and used for future application. So I would stop and conclude in here is that we have developed a toolbox both for mammalian and environment tox endpoint modeling. And we have a database, we have PPK model with the GUI to describe the pathway from exposure to dose. We have the in vitro dosimetry model to explain the accumulation of particle in an in vitro setting. We have QSAR model for the dose response. We've shown you how we extrapolate between in vitro and in vivo, as shown with the DQ12 quartz. We have also done environmental tox modeling, so there are tools in there for environmental tox as well. And we have demonstrated the use of high throughput system to generate data for modeling. So that in a summary is the achievement of work package 6 and all the quantitative tool for modeling the exposure dose response relationship.